Hi everybody, welcome to another video in differential equations, section 4.2 and 4.3, homogeneous linear equations. Actually, I combined these two sections together because they should be in one section because it's just one concept. This is one of the most important concepts in differential equation. That I hope that should be the last thing you forget about this class. Right, homogeneous linear equation. So in this case, we focus on the homogeneous linear second order equation. So first of all, we know the second order, meaning the highest order derivative, is second derivative. It is linear because there's no the derivatives and the function do not raise to any power. If let's say we have then this is no longer linear. Or if we have sine of y, that also not linear. We're not worry about that. We worry only about linear equation. Right, constant coefficient. So the coefficient is constant. The coefficient are constant. We're not talking about anything like this either, because the coefficient multiplied to the function or derivative have to be constant. So we don't have that in this case either. And finally, homogeneous, meaning that the right hand side is equal to 0. If it is non-homogeneous, then the right hand side is not equal to 0. So non-homogeneous equation is where there's the function on the right hand side that is not equal to 0. Right. Now, once again, we focus on this equation, which is homogeneous because we have 0 on the right hand side, linear because the function and derivative are linear terms, second order, highest order of the equation is the second derivative with constant coefficient. Those are constant coefficient. So there are a lot of things that involved in this equation. Now, with that equation, now we work on how do we get the solution of that. Now, first of all, let's consider the equation, the solution in this form, E2 or T. By the way, the solution, even though in here it is set of variable of x, but in the book they prefer to write the variable, the independent variable is t, so we write y is a function of t as a solution. So in this case, r is the constant. Well, before you ask why do we know the solutions like that, well, I'll get back to you on that in a few minutes. But if the solution is in that form, we can take the second derivative, the first and the second derivative. So that is the function. Now we take the derivative and then the second derivative. And we just substitute in, this is the second derivative, first derivative, and then the function. We just substitute that into the original equation, into the equation there. Right, and then once again we will factor out e to the rt common factor. We're going to have ar squared plus br plus c, exactly what we did in the previous section. Next, we have e to the rt. So what is the graph of exponential function? So consider that this is the graph of exponential function. y equal to e to the x. Look like this. So what's so special about that? So exponential function look like that. Of course, if it is negative, then it goes the other way around. But the point here is this is going to be greater than 0. It only equal to 0 when the variable goes to negative infinity. So but in general, it's going to be positive. Now, we know that it is positive. A positive number times something equal to 0, the only thing that could happen is that this has to be 0, right? Because e to the rt is not going to be 0. If we want 0, this has to be 0. So this must be 0, because that's not going to be 0. And so from there, from this equation, we go to here. And this equation is called, in the book I think they call auxiliary equation. Some other books call this characteristic equation. But later on we call characteristic equation for something else. So let's call this equation auxiliary equation. One thing to note that this equation, the coefficient are a, b, and c will correspond to a, b, and c. So second derivative r square, first derivative r, the function is a constant. So we match the original differential equation into auxiliary equation. Right. And then quadratic equation, this is the solution. So the solution is in this form. Right. Then we say, get back to the question, why do we know the answer is like that? Well, my answer is we guess. And then according to this theorem, the solution that we guess is unique. In that case, this is the only solution, right? So it's not the idea, we did not prove that directly, but indirectly we guess a solution and we show that it is the only solution. Then that is good as finding the solution directly. Right, so a theorem. For any real numbers, a not equal to 0, because if a equal to 0, we don't have the second order differential equation anymore. So a is not equal to 0. B, C, T naught, Y naught, and Y1, all of them are constant. And there will be there will be a solution that is unique for the initial value problem for all the t from negative infinity to infinity. So the solution that we guess could work. The solution we guess, if it works, it is also unique. That's my point. Right. And then you say, why do we have two solutions? How is that unique? Right. I'll get back to you on that in a few minutes. Right. So we know the condition for the equation to have the unique solution for initial value problem, have unique solution. Right, because that have to be corresponding to the initial condition as well. Right. So that's what we have. Before we go to the why there's two solutions, and then we said the solution is unique. Now let's go to this first. A pair function y1 of t, y2 of t is said to be linearly independent on the interval I if neither of them is a constant multiple of the other. Sounds simple enough. For example, if I say y1 of t is equal to sine of t and y2 of t is equal to cosine of t, they are not multiple of the other, then they should be linearly independent. But there should be a better definition than this, right? Because usually the better definition is something that is not in the negative term. By that I mean the definition should not say if neither of them is kind of a negative meaning or negative term. Usually the definition is should not be in that case. The definition would be better if it is not in the negative term. Right, so now we have another definition of linearly independent. y1 of t and y2 of t are linearly independent if y1 y2 prime minus y1 prime y2 not equal to 0 for every values of t. So once again, it is in the negative term when it said not equal to, but at least this time we have quantitatively, we can say if they are linearly independent or not, just based on this. And this have to be not equal to 0 for every values of t. Right. If there is values of t that work, then for this to work, it is equal to 0 for some values of t, then it's not going to be linearly independent for every values of t. Right. So the left hand side can be written as a wrong skin of y1 and y2. So in particular, the wrong skin of y1 and y2 is this 2 by 2 determinant. Of course, 2 by 2 determinant we can just cross multiply. It's going to be y1 y2 prime. So this direction, subtract the other direction, but which is exactly is that. So if the wrong skin is not equal to 0, they are linearly independent. And the function are linearly dependent if they are not linearly independent. So independent and dependent, because they complement or opposite to each other. Right. Of course, we get back to this. But now how do we write the solution? It says that if y1 of t and y2 of t are any two linearly independent solutions, then this a constant c1 and a constant c2 multiplied to y1 and y2 is a solution. Later on we call this is a complementary solution. But what I will mention a lot, the right hand side here is a linear combination of y1 and y2. So this is said to be a linear combination. So now get back to the answer. To answer the previous question that we have, we say if the solution is unique, then why do we have two of them? Well, this is not actually two of them. When we have two of them that are linearly independent, then we can write this as c1 y1 plus c2 y2, a linear combination of y1 and y2, or it's going to be c1 e to r1t or c2 plus c2 e to r2t. Now, this solution is unique, meaning that c1 and c2 are unique if we have a unique initial condition. If we have the initial condition, if those are constant, of course. So this solution with a particular c1, c2 will be unique if it satisfies this condition. Right. So once again, we guess a solution, and we can show that that solution is unique. So that's as good as find the solution directly. Right. So how do we actually find the solution? So find the general solution for that one, for this equation, so that the solution y1 and y2 are linearly independent. So how do we do that? So the first step is Let's check second order, right? Check linear, check. They don't have any function of y not. I mean y prime and y double prime. Coefficient are constant, which is good. The right hand side equal to 0, meaning it is homogeneous. When all of that, check out this equation corresponding to the auxiliary equation. Auxiliary equation. We have 1 second derivative replaced by r squared. First derivative replaced by r, and the function becomes just a constant. Yes. So when the equation is homogeneous, linear, second order with constant coefficient, when we have all of that, then from the equation we write the auxiliary equation. And of course with that solution, and y equal to e to the t is the general solution. We don't even need that, just go straight to auxiliary equation. Like this is easy. We just need to solve this equation. R plus 2, R plus 3. If we factor, that's what we have, right? So it doesn't matter how you solve the system, the quadratic equation. This should be simple. Right, so r equal to -2, r equal to -3. So let's say r1 and r2. Right, so we say the auxiliary equation is in that form, where the solution is y equal to e to the r t. So we have r1 and r2. When we have that auxiliary equation, then we have solution. We can write y1 is e to the rt, so it will be e to -2t, and y2 e to -3t. Just like that. And the solution general solution y, or we call the complementary solution, c1 y1 plus c2 y2, a linear combination of y1 and y2. So we have e to the -2t plus c2 e to -3t. So that is the solution. Simple enough. By the way, we can only do this if the solutions are linearly independent, right? So we don't need to check they will be linearly independent, but on this one, the first problem, we should check. So he check that y1 and y2 are linearly independent. Right. So what we do is we find the wrong skin. Will be y1, y2, y1 prime, y2 prime. We evaluate the 2 by 2 determinant, and if it is not equal to 0 for every values of t, then we say they are linearly independent. Right. y1 is that. y2 derivative negative 2 e to negative 2t and negative 3 e negative 3t. Yeah, just take derivative of that. Now, determinant, meaning we do the cross multiply. Do multiply that direction, subtract, but we multiply the other direction. So e to negative 2t times negative 3 e negative 3t, subtract the other direction, e to negative 3t, negative 2 e to negative 2t. I'll just multiply it out. When we multiply these two things with the same basis, just combine the exponent, right? And then with the negative 3, so we have negative 3 e to negative 2t and negative 3t, that's negative 5t, negative plus 2 e to negative 5t, and combined we have negative e to negative 5t. Now, what did we say about exponential function? Exponential function is positive or not equal to 0, right? So we do know that exponential function is positive or not equal to 0. So this one is not equal to 0 for every t. Now, if the Wronskian is not equal to 0 for every t, then it is linearly independent. So we check that if it is linearly independent, and the answer is yes, they are linearly independent. So we can write the solution as a linear combination. That, because if they are not linearly independent, one of them are multiple of the others, meaning that we can just combine like terms. Right, so simple enough. Most important here is, of course, is this. From the equation, we have auxiliary equation, and then solve for that, and then we can write the solution. Just a quadratic equation, and then we write the solution. Right. Now, the reason I combine the two sections together, because in the book they have the first section, I think they have the first two cases, and the last cases is in another section, but I think all three cases should combine together into one. So once again, we have homogeneous linear second order differential equation with constant coefficient. If we have all of that, then the equation, we can write this as the auxiliary equation. Right, which is auxiliary equation, which is a quadratic equation. And quadratic equation, we have three cases. The first case is where the solution are two distinct roots. And I forgot the important things here are two real distinct. The first one is real. Yeah. If two solutions are distinct real roots, then we just have y1 and y2 as e to the r1t, e to the r2t. Next, if r is the repeated root, so if we have only one solution, then we have e to the rt, and then we have to multiply t to it. And then you ask, why do we have to multiply by t? And my answer is, if we don't multiply by t, the solution will not be linearly independent, because we only have one. We cannot say e to the rt and e to the rt. They will be identical. So we have to make them different. By different, I mean linearly independent. We have to multiply by t to it. because we can show that they are linearly independent. In fact, I think I'm going to do this quickly. So we have Wronskian. One of them is e to the rt, the other one is t e to the rt. Right, take derivative or e to the rt. Derivative of this is the product rule, e to the rt plus t rt e to the rt. Yeah, derivative of the second term, e to the rt is r e to the rt times t. Right, cross multiplying, we will have rt e to the, sorry, that times that, e to the rt square or e to the 2rt times that plus rt e to the 2rt, subtract the other one, rt e to the 2rt. Cancel this, we left with only this. And because once again exponential function is positive, so that's why this is not equal to 0 for every values of t, and therefore they are linearly independent. Right? So just take derivative, product rule, and then we have that. Right. And we did show that one of the example here, these two are linearly independent. These two we just show are linearly independent, and later on we will show that these two are linearly independent as well. So if we have the complex conjugate solution, because this is a quadratic equation, if the solutions are complex, they are conjugate to each other, meaning the real parts are the same, the imaginary parts are opposite. Or usually we just say it, in this case we will have r1 2 equal to alpha plus or minus I times beta. So the solution can be written in this. In that case, we have e to the real part times t and cosine and then sine for the imaginary part. Right. Suddenly we'll do this example and we'll show that they are linearly independent. But finally, for each of these cases we have two, and those two solutions are linearly independent. So we write the solution as the linear combination of those solutions in each of the cases. Right. So this is what we need to know for those two sections. Right. Before we actually do some examples, now show that the function y1 and y2 are linearly independent. So the case number 3 here, we're going to show that this solution are linearly independent. Right. In that case, we will compute the Wronskian y1, y2, y1 prime, y2 prime. y1 is that e to alpha t. I try to write small, we might not have enough space. Right, I'll take derivative. We'll take derivative of that. We have y1 prime. That will be a product rule. So give us alpha e alpha t cosine beta t, subtract e to alpha t. The reason this is negative because that is derivative of cosine, which is negative sine beta t. And don't forget, the chain rule says we have to take derivative of beta t, so which is a beta. Right, so that is y1 and y1 prime. Now y2 is e alpha t sine beta t. We check derivative also using the product rule. So this is going to be alpha e alpha t sine beta t. Derivative of sine just cosine. So e alpha t cosine beta t, and then times beta. Right. And this say we have to write very small, right? Right, cross multiply. Right. Now, if we have those two terms, multiply this to this. By the way, the reason I have e to the 2rt because e to the rt times e to the rt is e to the rt plus rt. So that's why it gives us 2rt. So we do the same thing here. So that gives us alpha. The first term is alpha e2 alpha t. I mean 2 of them, right? When to multiply 2 alpha t, and then cosine, and then sine. And then that term times this. There's a coefficient beta at the end. So beta e to 2 alpha t. Cosine times cosine is cosine square. Beta t. Right. So that's where we multiply these two terms. Now, of course, we subtract the others product. Right. So so times that we have alpha e to 2 alpha t cosine times sine. And then negative, that term times negative, this term is going to be a plus. Also beta e to alpha t sine times sine will be sine square. Right. These terms are the same. Of course, e to the 2 alpha t, so they cancel out. So we end up with beta e to alpha t cosine square beta t, and these two terms actually the same, so we can combine like terms. Of course, I mean the like term that doesn't have the cosine. So both of them have beta e to the 2 alpha t factored out. Then we have cosine square plus sine square in the parentheses. And of course, Pythagorean identity cosine square plus sine square is 1. So that's why we just have beta e to alpha t. Once again, exponential function is not equal to 0. So this is not equal to 0 for every t. So if they are not equal to 0 for every t, so they will be linearly independent. So which shows that if the solution in this form, they will be linearly independent. Right. Now we have a few examples here, and all of them, of course, in the same form. Just go over different cases of solution for the quadratic equation. So first, solve this homogeneous linear second order differential equation with constant coefficient. So there are four things: homogeneous equal to 0, second order, yes, linear, yes, constant coefficient, also yes. So there are a lot of things that go into this. But if this is the case, then the equation will turn into homogeneous, the auxiliary equation. Once again, the second derivative go to r squared, the first derivative go to r. If we have y, it's going to 1. So let's just say it. If this is the equation, second derivative turn into r squared, the derivative turn into r, and the function turn into 1. So that's why it is 6. So the auxiliary equation corresponding to the differential equation is that. Right, so we have that. The equation factor out r squared plus r equal to 0, factor out r, we have r times r plus 1 equal to 0. So solution is 0 and negative 1. Or we say r1 is 0, r2 is negative 1. So we write the solution. y1 is e to the r1 of t. r1 is 0, e to 0 power is equal to 1. So that's why this is equal to 1. The other solution, e to negative t. Therefore, linear combination of these two, c1 times 1 plus c2 times e to negative t. So that's what we have. So very straightforward, right? Differential equation, go to auxiliary equation, solve for it, write the solution. Pretty much it. Right. This solution is a little more complicated because we have the initial condition, so we need to check. So in this case, it's actually very long, so I will write very small. In fact, I will just write into columns. Right, first thing, of course, from that differential equation, the first thing we write is the auxiliary equation corresponding to it. Auxiliary equation, second derivative, r squared. First derivative, r. The function, so it's just constant, times 1 if you want to. Right. And then solve for it. Of course, if you cannot factor, use quadratic formula. In this case, look like it can be factor. So the factor is minus 4, so that should be minus 5 and plus 1. Minus 5 and r plus 1 equal to 0. So simple enough, we can get r equal to 5 or r equal to negative 1, right? R minus 5 equal to 0, and then r plus 1 equal to 0. Just 1. R minus 5 equal to 0, and r plus 1 equal to 0. So if r equal to 5, and r equal to -1. And since they are different, so let's say r1, r2. Right. Of course, if you call this r2, that one r1, perfectly fine. Right, so we have that. Next, we write the solution. So these are two real distinct solutions. So the solution will be y1 equal to e to the r1 t e to the 5t, y2 e to the r2t, so e to the -t, -1t or just -t. And of course we can show that they are linearly independent. On this case we don't need to, but we write the solution as a linear combination of these two, c1 y1 plus c2 y2. So c1 e to the 5t, c2 e to -t. Right. So this is what we call a general solution, or later on we call that a complementary solution. Right. But in this case we have the particular, the initial condition. So first, initial condition. First, when this will be easier if one of them is 0, but this is not. Y of -1 equal to 3. Right, what we do, because we're going to put -1 into t and we make the whole thing equal to 3. So y equal to c1 e to t equal to -1, so 5 times -1 plus c2 e to t is equal to -1. And of course this is equal to 3, so y equal to 3. Right. Let's just put -1 for t. Right, so in this case we will rewrite this as c1 e to -5 plus c2 e -1 times -1 is 1. I don't even need to write that, but I do write this equal to 3. So let's keep this for now. Now the other one is the other condition, y prime of -1 equal to 9. Right. If that is the case, before we actually put in the numbers, we have to take derivative. If this is y, y prime is equal to, I'll take the derivative of this function. The derivative of e to the 5t is 5 e to the t, so it's going to be 5c1 e to the 5t, and derivative of e to -t is -e to the t, so this one gives us -c2 e to -t. We take derivative first. Now we put in the numbers. 9 equal to 5 c1 e 5t is equal to negative 1. So I put negative 1 in for t and make them equal to 9. C2 e to negative 1 equal to 9. Rewrite this, I will have 5c1 e to negative 5 minus C2 e equal to 9. Now this is the second equation. Now put this equation together. I'm going to write this is 1, this is 2. So 1 and 2 give us this equation. C1 e to negative 5 yeah, it is a plus C2 e equal to 3 5c1 e to negative 5 minus C2 e equal to 9. Right, how do we solve this equation? Actually, what you see is these two are the same, right? And these two are the same. So instead of write that equation, or we can write, let's use u and v for that. U plus v equal to 3. And then 5 u minus v equal to 9. Right, system of equation, two variables, should be able to solve for that. So if we add side by side, here v and v cancel out, we have 6u equal to 12. So u is equal to 2. Simple enough, right? Just add side by side, v and v cancel out, 6u equal to 12, so u is equal to 2. Now if u equal to 2, substitute back in here. U plus v equal to 3, so u is 2, plus v equal to 3, so v is 1. So if u is 2, v is 1. Now that's easy. Finally, u is equal to C1 e to negative 5. That is equal to 1. Well, u equal to 2, right? Sorry. So how do we solve for C1? To solve for C1, we will let 2 divide by e to negative 5. Of course, divide by the number move to the top become positive, so that e to the 5 power. So that's how we solve for u. And I'm sorry, that's why we solve for C1. Now v is equal to 1, and v is equal to C2 e is equal to 1. So C2 is equal to 1 over e. Or we write this as e to negative 1. Right, so we have C1 and we have C2 finally put into the equation. So the solution is y equal to C1 is going to be that 2 e to the 5th e to the 5t plus C2 e to negative 1 and e to the negative t. Of course, we can combine this. We say 2e to the 5 plus 5t and e to the negative 1 minus t. So this is equal to 2e to 5 plus 5t. Yeah, just combine the exponent. And then plus e negative 1 negative t. Right, so we can write the solution like that. So, of course, the point here is just write the equation in the auxiliary equation. So for that, write the solution. If we have initial condition, then we put in the numbers and we solve for that. And this is what we have. Right. Right, more samples. Solve the initial value problem. So once again, initial value problem look like long problem. So let's write the answer in 2 columns. Of course, first, differential equation, homogeneous equal to 0, yes. Second order, yes. Constant coefficient, yes. And of course, it is linear. So we can write the auxiliary equation. By the way, if this is equal to 4, either it's a typo or we have to do that differently. It's always have to have a constant. If it's not, then of course that was equal to 0. But if it is y, then we write that as a constant. By that I mean, so second derivative r squared, derivative r, the function constant equal to 0. Right? Now, to solve for it, and of course this is a perfect square trinomial. We can factor it. But they are the same, so we write that equal to 0. So when we solve for this, we have r equal to negative 2. And there's only one solution, so we call this as the double root. Or we will write this as r1 and 2 is equal to negative 2. Right, so that is the solution. That is the auxiliary equation and the solution. Now we go to the solution to the differential equation. Right. This is the case where we have the repeated root. So when we have repeated root, how do we write the solution? So we have repeated root, we write the solution as e to rt, and then to make it linearly independent, we will multiply a t into it. So r1, r2 are the same. So we write y1 is equal to e to the r. I just write r t e to negative 2t, and y2 I'll have to stick a t to it, so make it so it will be linearly independent. T e to the rt, so t e to the negative 2t. of course, the solution actually a linear combination of these two. C1 y1 plus C2 y2, meaning that C1 e to the negative 2t and C2 e to that's t e to the negative 2t, right? So this is the general solution, right? Now we have initial conditions. The first one, y of 0 equal to 1. It will be much better when we have the initial as 0. So this is the solution. I'm just going to put 0 in for t and make that equal to 1. So y will be equal to 1. C1 e to negative 2 times 0 plus C2 t is 0 e to negative 2 times 0. So we write this e to 0 power is 1. And this one has a 0, so that cancels out. So what do we have here? That's equal to 0 because times 0, and that go to 1. So we just have C1 is 1. Like I said, when one of them is, when the initial condition is 0, it is a lot easier to solve for. Right, so that's the first part. I need to zoom out. So, is that better? Yeah. So that is one of them. Now the other case is where derivative is equal to 3. So if this is the solution, I will just take the derivative of it. Derivative of the first one, C1 negative 2 e to negative 2t, and the second one I have to use the product rule. U times v, so u prime v plus uv prime. Plus u prime will be C2 e to negative 2t, so that is u prime v, then plus u v prime negative 2 e to negative 2t. So that gives us negative 2c1 e to negative 2t plus c2 e to negative 2t, and that negative 2 c2 t e to negative 2t. Right, now I'm going to make that equal to 3 and put 0 in for t, and also we know c1 is equal to 1 as well, so we substitute everything we know. When we substitute in this one, we know now c1 is equal to 0. Glad I write that in pencil. Equal to 1. Right. Now put in, make that equal to 3. The derivative equal to 3 when we put 0 in for t and 1 in for c1. So e2 e to the negative 2 times 0 plus c2 e negative 2 times 0 minus 2 C2 0 is for t e to negative 2 times 0. Now because of 0 here, that go to 0. E to 0 power is 1. E to 0 power is 1. So we have 3 equal to negative 2 plus C2, because that's just 1 and 1, that's 0. So of course here C2 is equal to 5. So we have the C2 and C1. So the solution y equal to C1, which is C1 is 1 and C2 is 5. So C1, I'm going to put 1 here. E to negative 2t plus C2 is 5. E to the five t e to negative 2t. Right, simple enough. So that is the solution. So that's what we have. Simple enough, right? Right, so we have two cases already. So the first case where we have two distinct roots, two real distinct roots, those will be the solution. Now if we have repeated root or the double root, okay, so double root or repeated root, then we have this case where we stick a t to it, stick a variable to it, so to make it linearly independent. We did show that it is linearly independent. Simple, because this is just the solution, no initial condition. So just go to the solution here. Right. Auxiliary equation. Second derivative r squared. First derivative r, y or the function, it's going to be just a constant. Right, now try to factor. Can we? To get to 10 is a 1 times 10. It's not going to give us 6, or 2 and 5 also doesn't matter. It's not going to give us 6. So it looks like we cannot factor. So if we cannot factor, or even though if we can factor, we can always use quadratic formula. Right. Once again, even though if we can factor, we still, the quadratic formula always work whether we can factor or not. But in this case, because we cannot factor, so this is the only option. Of course, we can do completeness square as well, but I consider that will take more work. So that is quadratic formula. Negative b, just write down the coefficient here, h1, b6, and c10. So negative b, negative 6, plus or minus b squared minus 4a and c over 2a negative 6 plus or minus square root. 6 squared is 36 minus 40. 36 minus 40 is negative 4 and 2. Right. So we don't work with complex number often, but when we have, let's say if we have m, let's say m is positive. When we have square root of a negative number, the negative inside square root will be written as an I imaginary outside of the square root. So we take the negative inside the square root, moved outside, it becomes the imaginary number I times square root of that number. So here we have the negative inside the square root. That gives us an I outside the square root. So that gives us negative 6 plus or minus square root of 4 is 2i. Right. Now, whatever you do not cancel the 2 here. That's totally wrong. Because whenever we cancel, it has to be a factor. Right? So, meaning if it's multiplied, we can cancel. If it's plus or minus in the middle, we cannot factor. Cannot simplify. But both of them are even. So I can pull out the 2. Factor out the 2 on top, we have negative 3 plus or minus I. Yeah. Once we factor out the number, then we can simplify. Right. So that is the solution. So we have R1 and 2 is negative 3 plus or minus I. Right. Usually if it is complex solution, I'm going to write together like this. Right. Case number 3. If the solution in this form, then we have e to the real part plus e to the real part and then cosine and sine of the imaginary part. So in that case, if we write as negative 3 plus or minus I times 1. Right, so that is the solution. That is the solution to the auxiliary equation. Now we write the solution. Right. Right, so be y1 will be solution to the first part, the real part, e to negative 3t. And then for the imaginary part, we have cosine of 1t. In fact, let's write in the general form first. E to alpha t and cosine beta t. So if we make this equal to alpha plus or minus beta I. So obviously what we have here is alpha equal to -3 and beta equal to 1. So the solution will be e to alpha t cosine beta t. So e to the real part times t, and then cosine of the imaginary part. Or y2 equal to e to alpha t, and then sine. Right. So pretty much one of them is sine, one of them is cosine. You can interchange 1 and 2 here. So it doesn't have to be y1 have to be cosine, and y2 have to be sine. Of course, you can switch them. Right. Now switch, put in the numbers -3 for alpha, cosine of 1t, e to -3t, sine of 1t. So e to -3t cosine t, e to -3t sine t. Of course, we put them together as a linear combination to have the solution. C1, Y1, C2, Y2. So be C1 e to -3t cosine t plus C2 e to -3t sine t. Right, so I write a little more details than I should, but that's what we have. Right, so when we have the imaginary solution, that's how we write the solution. Right. Of course, I can show why the solution is in that case, but of course, if you write the solution like this, it's not e to alpha plus beta I times t, or e to the alpha minus beta I t. It's not wrong to write solution like this, but with a lot of complex operation, a lot of algebra in complex number, we can simplify this to the cosine side. That takes too much work, so I'm not going to do that in class, but it can be shown that this and these two solutions equivalently can be written in terms of the cosine sine that we have there. Right. Now, we have similar problem, but this time we have the initial condition, so this will be a little more work, obviously. So once again, I write in 2 columns. So first, auxiliary equation. Right. For once, I just want to spell it out. Right. Now, auxiliary equation. Second derivative is a square. First derivative is the first degree. The function of 0 degree, meaning r to the 0 power. Of course, you can just write that. R square to r to the first plus to r to the 0 power. To 0 power is 1. Yeah, so certainly we can do that too if we want to. But we just say 2. Right. that. Right, try to factor. If it is 2, it has to be 1 times 2. And there's no way we can combine 1 and 2 to give us 2. I mean, add or subtract 1 and 2. There's no way we can get 2 from it. So, quadratic formula. Like I said, even though if you can factor, quadratic formula always works, whether we can factor or not. Right, A is 1, B is 2, C is 2, so negative 2 plus or minus square root B square minus 4 A C over 2 A. Right, we write this negative 2 plus or minus 2 squared is 4 minus 8, so that is minus 4 over 2. So equal to negative 2 plus or minus. Once again, negative inside square root, that is imaginary. So that gives us negative 2 plus or minus 2i over 2. Once again, do not cancel the 2 here. Factor and then cancel. Both of them are even. Both of them are divisible by 2. So I'll do that. Put out the 2. Negative 1 plus or minus I. Yeah. Factor out 2 on the top. Cancel with the 2 at the bottom. Right, so that is the solution. R equal to negative 1 plus or minus I. 1, 2. Right, so that is the solution to the auxiliary equation. Now we will write the solution. Right, so we have the real part and the imaginary part is 1. So the solution, so this was equal to alpha plus or minus beta I. So alpha is negative 1 and beta is 1. Alpha is negative 1, beta is 1. Right, so the solution y1 equal to e2 alpha t cosine beta t. So e to negative t cosine of beta t or just cosine of t. y2 e2 alpha t sine of beta t. So e of negative t sine of t. And the linear combination of these two. C1 y1 plus C2 y2. So we have C1 e to negative t cosine t plus C2 e to negative t sine t. So that is the general solution. Now we do have initial condition, so this will work. Of course, I can zoom out further, but it's kind of difficult to see. Right, so we have this initial condition. So first, y of 0 is equal to 2. So obviously, of course, we're going to put 0 in for t and make that equal to 2. 2 equal to c1 e to the negative 0 cosine of 0. Yeah, just put 0 for t, plus c2 e to negative 0 sine of 0. Right, so what do we have here? E to 0 is 1. Cosine of 0 also 1. That's not that bad. So that's why I've said usually if the initial conditions are given at 0, then that will be a lot easier to do. E to 0 power is 1. Sine of 0 is equal to 0. So that one gone. And so that's all we have is that term. So we have 2 equal to c1. Right. That's good. Now, the second initial condition is derivative at 0 equal to 1. To do this, we have to take derivative first, and that is not simple. Right. Derivative of this, this is going to be product rule. UV and then UV. Yeah, so we use product rule, 2 of them, so 2 product rules. So for the first one, U prime C1 negative e to negative t, that is derivative of e to negative t, and then cosine of t, and then plus c1 e to negative t, derivative of cosine is negative sine. That's the first term. For the second term, c2 negative e to negative t sine t plus c2 e to negative t, derivative of sine is cosine. Right, simplify this a little bit. Negative c1 e to negative t cosine t, and we cannot simplify any of this because this is, even though the like terms, but this is c1, this is c2. Yeah, we can combine like terms, but yeah, we're going to put the numbers in anyway, so it's not going to be a big deal. Right, minus c1 e to negative t sine t, and then minus c2 e to negative t sine t plus c2 e to negative t cosine t. Right, now put in the numbers 0 and 4 t and make that equal to 0. I'm sorry, 0 and 4 t and make that equal to 1. 1 equal to negative c1 e to negative 0 cosine of 0 minus c1 e to negative 0 sine of 0 minus c2 e negative 0 sine of 0, c2 e of negative 0 cosine of 0. So it's not that bad. We already know that c1 is equal to 2. So we put c1 equal to 2 later. But first, sine is equal to 0. So that one cancel, that one cancel. So it's not that bad. E to 0 power is 1. Cosine 0 is 1. So when it's clear, we have 1 equal to negative c1. c1 is equal to 2. So put in 2 in for c1. Times 1 times 1, so that's just negative 2. 0, 0, c2 times 1, so that's just c2. So from here, c2 must be equal to 5. I don't know why. Mean 3. So c2 is 3, and c1 is 2. Substitute back into this equation. So we have y equal to c1, 2. E to negative t cosine t plus c2 is 3 e negative t sine t. Right, so that's what we have. So it's not that bad. Just be mindful when we take derivative of this, it has to be a product rule. Right, and then so auxiliary equation, we have complex conjugate solution here. So the solution must be that linear combination. Initial conditions, so for that we have C1, C2. Substitute back into general solution, we have particular solution. Right, next. Now we have something more. Find a general solution for third derivative plus for y second derivative equal to 0. So we will do this in chapter 5. But for now, for this we can write the auxiliary equation. Third derivative, of course, is the third power. Second derivative is the second power. Now if we solve for r, we can factor out r squared. So we can solve for r. So r squared equal to 0. And r plus 4 equal to 0. So if r equal to 0 here, and that is the double root. Later on, if it's double root, we just say r1 and 2. So there are two solutions that have the same values as 0. And the other one is negative 4. So yeah, I just want to put this example just to show that it doesn't have to be a second order. For higher order, we still can write the solution based on the three cases that we have. So auxiliary equations that, and then solution. So we can write y1 is e to the r1 times t, which is e to the 0 power times t, or e to the 0 power, which is 1. Once again, I don't have to write all of that. y2 because those are the same solution, we cannot say e to the r2. We have to make it linearly independent. So it will be e to the r2 or r1 t times t. Have to make it linearly independent. So that gives us t e to the 0t. E to 0t is 1, so this is t. And r3 is -4. y3 is e to -4t. y3 equal to e to r3t, or e to -4t. And finally, so we have y equal to c1 times y1, which is 1, plus c2 times y2, which is t, and c3 times y3. Right. So this just shows that the method of the linear equation can be extended to more than just a second order. Let's say we have higher degree of the auxiliary equation. If we have repeated root, we just stick a t to it to make it different. If we have the triple root, then we have 0. I mean, if there's 1, 2, and 3, if that 3 solutions are the same, we stick a 2 in the first one, stick a 2 square on that one. So just want to write this quickly. Let's say if we have R1, R2, and R1, 2, and 3 equal to 5, for example, then the solution will be e to the 5t, t e to the 5t, and t squared e to the 5t. So it depends on how many solutions, how multiple of the solution we have to stick the power of t to make them different. By different, I mean linearly independent. Right, but we do this kind of problem later. I just want to put that here for now. Right. So once again, the most important thing in this section, of course, the 3 cases of solution, and you have to know that. Right. I stop the video here. As always, thank you for watching. See you in another video in differential equations.